Okay, this week we're going to begin talking about the energy that's needed to drive the atmospheric system that we have in our world. So, where is this energy coming from? It actually comes from a couple sources in a way. All of it comes in from the sun, but then the terrestrial radiation plays a role as well. So, we're going to talk about radiation this week. We're not dealing it in depth. We're not going into much in the way of math with it. So, we're just trying to get you familiar with a little bit of where this energy comes from and why things are different in the atmosphere. So how does the energy flow into and out of the atmospheric system to maintain a stable and habitable planet? That's a key part. It's habitable. So with that, we'll talk about the electromagnetic spectrum. What I want to show here with this is, notice right here, visible light. This is what we see. So wavelength, it's not very big, really. We see a very narrow wavelength. If the wavelength is shorter, we tend to go to the ultraviolet. If the wavelength is longer, it's heading toward the infrared. So if you were actually look at this, look at the picture here, you see red up to the top part, and you see more violet down to the bottom. And that's why we come up with the names of infrared. For red, for the longer, and ultraviolet for the shorter. So we got to talk about a little bit to understand what electromagnetic radiation is. We need to talk about wavelength. It is a wave. And since I think of it when I go to the ocean. You ever get hit by one wave after another in the ocean? A wave comes up, goes over your head, goes back down, goes down to your feet, then back up again. So in the time it takes for one wave to go by you, where it peaks, goes down to your lowest, 20 low, and back up, is considered a wavelength. In electromagnetic radiation, the more energy, the shorter the wavelength. The less energy, the longer the wavelength. Because all electromagnetic radiation moves at the speed of light. So, now, something else that we need to understand is the world, all of it is a black body. It's literally very close to the same temperature if you averaged over the whole globe. And it absorbs all the radiation it receives, either in the atmosphere or whatever. And it's a perfect emitter as well. All the radiation's got to go back out. So that's a black body, and the Earth approximates a black body. So there is a law called Wend's displacement law. Well, what does that mean? Well, it's real simple, actually. It's the maximum wavelength is proportional to 1 over the temperature of whatever body's doing the radiation. So you think about the sun. The sun is extremely hot. So if you have the sun's radiation, you'll notice it tends to put most of the spectrum in the visible. However, the Earth, on the other hand, is more towards the infrared. So that's why we learn a little bit from Wend's displacement law. We can see where most of the radiation wavelength is coming from. So the other rule of thumb is the energy emitted by a black body is 10 to the 4th. Well, think about the difference in temperature between the Earth and the sun, and then multiply it to the 4th power. It's a huge difference in the amount of energy coming from the sun than comes from the Earth. So the other one is we call the inverse square law. Doubling the distance from the sun reduces the solar radiation by 1/4. So we consider Earth to be 1. So energy is 1 divided by 1 at Earth. So if you go out to 2 radiuses away from size of Earth, just substitute 2 in here. Basically, you're always going to be multiplying by 2 times 1. So you wind up with that squared. So if you were double the wavelength, double the distance out, and you could do it with 3 as well, or 4. Say you're 4 times our radius around the sun, it would be 1/16. So you can see the further out in the solar system you get, the amount of energy reduces very quickly. Here's the part where you really understand. Think about solar altitude. The altitude is the sun directly over your head, or is the sun coming into you from an angle? To demonstrate that, take a look at a flashlight. Put it on the surface. If it's straight overhead, you see it's a very concentrated circle. Having it at the same distance, but at an angle, look how much more it spreads out. It's the same amount of energy coming out, but it's covering a bigger area. So any individual point in here is getting less energy. And that is a key thing. Towards the equator gets a whole lot more energy than the further north you are, or the further south you are. And with that, you take it, whatever latitude we are, if you were 45 degrees north and the sun was directly at the equator, it would have an angle of 45 degrees. At the North Pole, it would literally be just skimming it. It would be, if you were there, you would feel like you have sunset or sunrise all day long. Now, as the sun moves, remember this 90 degrees is going to shift north or south here as the sun, since the earth is tilted. So instead of being 45 degrees in the summertime, this may only be 20-some degrees. However, if it was in the wintertime, it might be more like 60-some degrees. And with that in mind, you can see how temperatures fluctuate. Singapore, very close to the equator, not much change over the year. New York, further north, 43.5 degrees north. Pretty strong influence of the sun here. And if you were at the Antarctica, sun doesn't shine there for 6 months of the year. So you can see where that happened. One of the things I want you to think about too, with the rotation of the earth around the sun, it is tilted the same exact way all the way around. So when it's here, the sun is on autumnal and March equinox, which is where we're coming up to right now. The sun comes directly in to the center of the earth, right around the equator. But when it gets to the winter solstice, our top is pointed away, so you have less energy in the northern hemisphere and more energy in the southern hemisphere. Summertime, just the opposite. So all this has to do with the distribution of solar energy. Now, in order to understand all of solar energy, you also got to understand that in the atmosphere, there are certain things that keep the energy from Earth, or even the Earth itself. Some of it is absorbed by the Earth and by the atmosphere. Some of it's reflected. A cloud would reflect sun back. So would snow cover. And the Earth transmits so much energy back out into the atmosphere and from there into space. So you can see here, for example, scattering at the top of a cloud. Some of the light goes back upward, some of it comes downward. Albedo, reflection. Think about it. Those clouds look white when you look at them on satellite. Absorption. Some of this might even be from different chemicals in the atmosphere or the Earth. The lighter the surface, again, the higher the albedo. So when it snows, you actually get less radiation at your house to be used for heating the air. So where there's snow cover, it's going to be cooler. Where there's no snow cover, it's probably going to be warmer. And here's the distribution. Reflected by the Earth atmosphere system is 30%. Absorbed by the atmosphere is another 23%. And finally absorbed by the Earth's surface, you need someplace to heat from, about 47%. So, with that, now we can go to talk about greenhouse gases. This is what makes it livable. If you took just what we just talked about there, our temperature would be significantly colder than it is. We do need greenhouse gases to keep us alive. So what do? They absorb infrared radiation. So when the Earth transmits infrared radiation back up to carbon dioxide or methane, it's absorbed by that chemical, and some of it is transmitted back down towards Earth, and some of it is transmitted back out into space. So with that, you wind up with a warmer Earth. So if we didn't have any greenhouse gases, we would be a number of degrees colder than we are. However, by the same token, the more greenhouse gases, the warmer we become. So there are all kinds of greenhouse gases. We talked about water vapor is actually a huge one. Carbon dioxide, ozone, methane. Methane is significant because it's 21 times more effective than carbon dioxide. So a little methane goes a long way. So we have a curve over the years, which they've been plotting out at Mauna Loa, of the carbon dioxide. Began in 1957. Not a long record. But the one interesting fact is it's going up faster and faster every year. It's not just a straight line going up. It's actually a curved line that's getting constantly faster. So that's just something to keep in mind with all of this. So with that, let's go look at a couple things. I just wanted to show you satellites take advantage of all of what you just saw there. There are certain infrared radiation from the Earth that goes straight through the atmosphere, never touches anything, it gets absorbed. And there are others that emit from different layers in the atmosphere. So they're actually visible in band 1 with 0.47 and band 2 with 0.64. Notice the one's red, one blue. They lean that way with it. You have an infrared that's near the surface coming up called Veggie. A high infrared, 1.3 microns. 1.6 is like snow and ice. Here you can see cloud particles. Here's another shortwave infrared. Here's upper level water vapor. So this is a channel looking at the higher levels of water vapor, up above about 20,000 feet. Mid-level, more like 15,000 feet. And then low level, about 10,000 feet. Then there's cloud infrared or ozone and clean. This one is the cleanest channel, which is 10.3 microns. It's not absorbed by anything. Then you have another long wave, 11, 12 here. And even a CO2 long wave. So you can see we take advantage of all of that when we're looking at the weather. So just looking, for example, at this image, which is called geocolor, which gives you a very high resolution image over the U.S., you can see all kind of clouds looking across the U.S., moving from west to east. I guess this is beta down here, old cold front down here that went through, and you can see some high clouds up over top of the southern part of West Virginia here. And here's a big storm. I think that's Teddy out there. But say you wanted to look at we'll just say moisture. So I just pick a moisture band, and let's look at the mid-level moisture, about 15,000 feet. This is really useful in forecasting because it gives you mid-level moisture, which is important for forecasting clouds and rain. So you can see here there's lots of moisture down the Gulf of Mexico streaming up. And looking at this, mid-level would say a lot of the clouds coming up into the West Virginia are probably around 10,000 feet. And then there's Teddy out here. And there's another low coming this way. But you also see this dry air right here coming in. That dry air actually comes out of the stratosphere. It's a dry layer coming in there because there's a jet going by. The very dry layer also coming in because some of this area down here is desert. So you can actually see one right here. It's probably the jet stream coming around the corner here. So all kind of interesting stuff you can get out of satellite because you understand in the atmosphere what wavelengths are available to use where. finally, just looking at the weather map today, we just got big high pressure pretty much over West Virginia, just the north of West Virginia, over the Great Lakes. Here's Beta. There's the cold front that passed through the other day, working its way south. But if you thought about it, with the radiation today, it should be cooler the further north you get, and boy, is it! It is really starting to cool up in Canada. Here's 43 degrees, 43 up here. So the sun is beginning to retreat away from northern Canada, so you're getting colder. Still pretty powerful down here in Florida. Still 80s down in there. So hope you get something out of this. Let me know if you have any questions.